Okay.
Okay, go ahead.
Cool. Yeah. Shout out Paymon, Justin, and Ben for giving me this platform again. But yeah, I just wanted to take a quick second again to plug the application for projects again for winter quarter. And yep, thanks Justin for putting that in the chat. So yeah, ACMAI Projects is recruiting for winter quarter. We're trying to make projects open and accessible, which means that we want everybody, even if you don't have a ton of experience, to hop in and try and contribute to our project. So we decided that if you took advanced track this quarter, you'd be eligible to be on the projects team for winter quarter. And since all of you guys have, you've made it this far, all you guys will be eligible to be on that projects team for winter quarter. So if being in projects is something that you're interested in, and I would highly recommend as the next step, after taking advanced track, please take a quick second to fill out that application. We ask you a few questions on the application. We ask for your resume just because we want to get an idea of how much experience people have. If the only thing you have on your resume for machine learning based experience is advanced track, that's totally fine. Don't worry about it. We're trying to make projects open and accessible to people that don't have a lot of experience. And yeah, we also ask you how comfortable you are with a few of the concepts that were taught in advanced track, because once again, we want to get an idea of, how much knowledge people are coming in with. But yeah, the application deadline is Sunday at 11:59 p.m. So it'll close at the end of the weekend. So please get your applications in, and looking forward to working with you guys next quarter. Ryan had a quick question. What kinds of projects would we be doing? So we haven't completely finalized the project yet, but it looks like we're going to be doing a leaf disease classification project. But I'll keep you updated on that because we haven't completely finalized it yet. If you're not sure whether you've applied or whether your application went through, feel free to just apply again. We'll remove any double applications manually on our own. Awesome. Yeah, if there's no more questions, I'm gonna go ahead and hop off. If you do have a question, feel free to, PM me on Discord or whatever works for you. So, thanks guys. Appreciate it, and shout out to Justin, Paymon, and Ben again.
Awesome. Thanks, Harsh. Okay. So yeah, thanks for that, Harsh. So yeah, I guess we should have started by saying hello, everyone. This is the last advanced workshop for this quarter. We are going to be recording this entire thing because last time for you guys who were watching the recording, we kind of cut off the recording after we explained the project, and we realized that might not be great for you guys who are watching the recording. So we're gonna try to record this whole one, and we're gonna spend like a little bit of time like going over the things that we kind of talked about last week, just as a review for everyone. So yeah, you guys should all be able to use that. Okay. Another thing I wanted to say is, so we finalized, I think for next quarter, we're gonna teach beginner track, advanced track, and advanced plus plus. So yeah, all of you guys are in advanced right now. So I don't know, like you probably don't want to. Yeah, I'll share them in a second, Justin. So you probably don't want to like go to beginner, but there's like some good stuff there anyway if you want. And then sorry, I'm just opening up the slides. Justin reminded me to do that. Okay, let me share the slides first. Okay, share. Okay. Cool. Okay, sorry about that. So here's the slides. What was I talking about? Oh yeah, we're teaching beginner, advanced, and advanced plus plus. So probably most of you, if you are interested in continuing, we are going to be teaching advanced plus plus for you guys. So it would be super cool if you guys wanted to come out to that. The people teaching it will be most likely like 99% confirmed, but not 100%. Me, Justin, and Varan. Varan taught apply. I think Varan taught apply ML this quarter. So if you like Varan, he's gonna be with us teaching advanced plus plus. And advanced plus plus, just to talk about it for a little bit to give you guys some information. So I think we're gonna have it so it's kind of like a bit more free form. Like it's totally possible we might have like someone like John, like our ACM AI president, or someone else like come in and just like give like a talk about a topic they're like super familiar with, because it's sort of more of like an advanced topics sort of class. And then we also like, the whole point is kind of for you guys to tell us the kinds of things you want to learn about, and then we can like, we'll kind of like dynamically create something, some sort of presentation to talk about that if we don't already have something on it. So it's like it's super fun, more free form. We talk about like some of the more advanced like models that are like commonly used in like industry and research and stuff. So yeah, I think it'll be a great time. So we encourage everyone to come out to that. Okay, awesome. So back to the project. So yeah, so you guys, uh, I'll just quickly go over it again. So the project is to create a CNN to perform a classification task on the CIFAR 10 dataset. So remember, the CIFAR 10 dataset is kind of like the MNIST dataset. So it has 10 different classes, except we have colored images now, and we're dealing with, much more complex tasks like classifying things that are not just handwritten digits. So yeah, so I mean, the assumption is most of you guys already knew that or have started working on this, especially if you were here last week. So yeah, I'm not going to spend too much time on the slides. I'm going to spend most of the time on uh, on the Jupyter notebook, and we'll kind of be able to do a dynamic discussion there. Okay, so I'm gonna go over to the Jupyter notebook. So this is part of the kind of code that we wrote when we were designing this workshop as kind of a template. So as you can see, some of the stuff is already filled out. So this is good, because and just uh sorry to get distracted, but can we make sure someone's in the breakout room, Ben or Justin? So like, if someone goes in there, we can answer their question. Yeah.
Yeah, I'm going to be recording right now, so I don't know if that affects the recording if I go into the breakout room. So I'm just going to
Yeah.
stay here.
Maybe Justin, can you go into the breakout room? Okay. Awesome. Um. Okay. So yeah, I'm I'm showing you guys like sort of like where I think most people like got to um last time, and then we're gonna talk about this a little bit, really go through it, and then we'll continue from there. Okay, so these are just the imports, right? This is what so these are all the kind of imports you need, all the packages. Um, Simple enough. Um, so here's what we talked about last week. So this is kind of common practice when you see like PyTorch code, that you'll usually see something like this. Um, and the purpose of this is basically saying, okay, if CUDA is available, so if you have like an NVIDIA GPU available on your machine, set the device to that GPU. Um, and then if you don't, then just set it to the CPU. And this is how we're kind of going to determine whether we're running on the CPU and the GPU, or the GPU. Now, like I said, you can't mix these two things. So if you have some tensors allocated on the CPU and some on the GPU, and you're doing operations between them, you're going to get a runtime error, because they're stored in different areas of the machine. They're in different places in memory, so they don't have direct access to each other. So you can't do computations with them together. So usually, like, we allocate tensors to the GPU only when we're doing our actual training loop, because that's where the bulk of the actual computation with the back propagation and updating based on the gradient approximations and whatnot are actually happening. So we usually are going to allocate tensors to the GPU at that point if we have a GPU available, and we'll kind of see that today. So that's that. Um, yeah, so this is us loading the CIFAR 10 dataset, right? So I'll quickly go over this. So we create an instance of like this torchvision.datasets.cifar10 like class, right? And then we pass in these following construction parameters. So we tell it the root is, I made this folder slash cifar10, like you can see it here, cifar10, right? So this is where the data is supposed to be stored if we already have it, or if we don't already have it, where we're going to download it. So yeah, that's what the root means. The transform, so the data doesn't come packaged as like torch vision 10 or PyTorch tensors, so we have to transform them to tensors. So that's just what this does. And then download equals true. So this basically will check like, okay, is the data already in Cypher 10? If it is, like, we're fine. If it's not there, then just download it into root, right? So we do that for the training set, and we do that for the test set. So yeah, so by default, like, there's also this parameter train, right? So train by default is set to true. So that's why I didn't specify it here. But if we say training equals false, this will give us the test data set. So yeah, I made a train data set and a test data set. And now that we have the train and test data sets, we need to construct data loaders, right? So like I said, we need the data loaders to actually iterate over the data, our training examples. So as I mentioned in the PyTorch workshop, the data loader is going to serve to lazy load the data. So it's going to make it so we can access the data much more quickly than we would otherwise. Two, it can construct batches from our data so if we just specify batch size 16, it'll already group our data into batches. So it'll basically reshape the tensors in order to accommodate like a batch size of 16, right? And we saw this in the PyTorch workshop. And then shuffle equals true, just shuffles around all the data, as you'd expect. Okay, so yeah, once again, like, ask any questions as they come up. Feel free to interrupt me. I think most of you guys like already got through this stuff, so I'm going through it kind of fast, so we have time to get to the new stuff. So yeah, let me just run these code blocks. So okay, yeah. So yeah, and then this part is just gonna print out an image, right? So if you guys were here live last week, we kind of talked about this in a lot of detail. This is very similar to that kind of code that we use to visualize the handwritten digits in the PyTorch workshop. So I encourage you to go back and look at that if you're a bit unfamiliar with this. But the idea that's different here is that we have 3 color channels instead of 1 color channel now, right? Because it's the colored image. So we have R, G, and B. And because of that, we want to represent the image in color. So if you guys remember for the MNIST one, we said CMAP gray. We added a thing here that says like CMAP equals gray. So we don't do that here because we want a colored image. But one thing that we do have to look at is this image.permute. So what image.permute does is it kind of swaps the locations of the dimensions. So it'll swap like the inner with the outer or whatnot. So let me explain that in more detail. So if we were to say image.permute 0, 1, 2, that would just return exactly the same tensor because the 0, so dimension 0, so the first dimension stays on the outside, dimension 1 stays in the middle, dimension 2 stays on the inside. Now, when we do image permute 1, 2, 0, this is basically saying take the values at dimension 0 and kind of shift them over to the innermost dimension. And the only reason we do this is because the matplot, it wants you to have the color channel as the innermost dimension here. So we just run this permute. If you don't do this, you'll get some like weird like thing that doesn't really make sense. So that's the only reason we run that, just because of the discrepancy between the way the tensor data is organized and the way that matplot expects it. Okay, so yeah, hopefully that stuff's clear. So now let's talk a bit about the actual model architecture. So we spent a lot of time talking about this last week. We especially talked about kind of how we get from this like the convolutional layers to the linear layers, because we have to do a little bit of a transformation there to get that working. So I think that's like what the hardest part was of kind of constructing the model. So if we recall, right, in our constructor, so in our init function here, all we're kind of doing is kind of like telling like are kind of laying out like, okay, what pieces are we going to use to construct this model? Okay, so it's not, there's no like organization here in terms of ordering, right? So I could have defined these things in any order here. This is just like kind of like throwing a bunch of materials on the floor. And then in our forward function, we kind of like piece those materials together in a way that makes sense. Okay, so so in my example, right, in my very simple kind of model, I have one convolutional layer that starts. So our input has to be 3 because we have 3 color channels, and then our output is going to be 6 for me. So that means we're going to do 6 feature maps, right? So the depth of the convolutional layer is going to be 6, and then the 5 is the dimensions of our filter. So this means I'm going to be using a square 5x5 filter to go over my input image. So ultimately, I'm going to get a convolutional layer that has a depth of 6, right? So 6 different feature maps. And then we do max pooling. So 2, 2 just means, I think, if I remember, that means it's a 2x2 filter. So, and then it's a stride length of 2. So that's exactly how we did max pooling, right? We had so the max pool 2D itself will inherently take the maximum value from each filter. So if we're using a 2x2 filter, it'll go over that 2x2 space, and then it'll look for the highest value and then pick that one out. So that's what the max pool does. And then, yeah, so we have a filter of 2x2 and then a stride length of 2, which is exactly the kind of idea we talked about in the CNN workshop, right? This is the common convention for how we do max pooling. So that'll kind of cut our width and our like height by like half, right, in each direction. And then but we're still going to have a depth of 6, right, because we still have 6 filters. Okay, so with that in mind, that's why our input is going to be 6 here. We have because we still have a depth of 6. Now I want 16 feature maps out, so I'll put 16 there, and then I'll continue to use a feature map of 5. Okay, so that's like the convolutional part. So I'm going to stop for a second and see if anyone has any questions about that part, and then I'm going to talk about like the rest of this after that. Okay, cool. Oh, someone, I saw you on mute.
Would you say again how the max pool to reduce dimension, is that what you said?
So like what I meant is like if for a single feature map, if the width is like, for example, 30 by 30, then, or if the width is 30 and the height is 30, so if it's like 30 by 30 for one feature map, then after you go through max pooling, right, you're going to have 15 by 15 because you have a stride length of 2 and you have feature maps that are 2 by 2, right? And I can actually show this in the CNN workshop, right? Let me pull it up. Yeah, so yeah, if we look at the pooling slides, right? So this was like how it works, right? So like if you have a 4x4 here, then you have then you're gonna get a 2x2 out, right? Because you have stride length of 2 and you have 2x2 filters, and you take the max value from each of those 2x2 little spaces. So did that help or?
I think I'm a little lost in details, but I think I get the idea.
Yeah, so basically like if you like the output of this convolutional layer, right, is going to be the input into this max pooling layer, right? So
Yeah.
if the output of this is, it's not 30 by 30 in this example. I don't think it is. But let's say it's 30 by 30 for one feature map. So if it's 30 by 30 for one feature map, then it's 30 by 30 by 6 for the whole thing, right? Because there's 6 feature maps. So then when you pass the feature maps through this max pooling thing, you're gonna where did it go? Okay. So you're gonna have a stride length of 2, and you're gonna have 2x2 filters. So each of these are like one section that the max pooling is gonna look at, right? So in our example that I was saying, it's like 30 by 30. Here it's like 4x4. So then you take the max value out of here. So the max value is 255 for this yellow square. So you put it 255 there. The max value is 0 for the red square, put it 0 there, so on and so forth. And then now you're left with a 2x2 thing. And this is for one feature map, right? So we have 6 feature maps. So if we came in with 30 by 30 by 6, and then we pass it through the max pooling, our output's going to be 15 by 15 by 6. Because we still have 6 feature maps. It's just we kind of compressed the data in each of the feature maps.
I see that.
Okay, cool. Yeah, Ben also just sent a thing in the slide, so
Yeah.
you can, or in the chat, sorry, so you can check that out. That's the PyTorch
Yeah,
link.
if you don't have the if you don't have our workshop slides up, the PyTorch documentation also has like a little formula there. I think we might have mentioned it last workshop. It just tells you like how to calculate the output dimensions based on different parameters like the stride, the kernel size, and stuff.
Yep. So I encourage you guys to look at that. Now, okay, the thing that was hard for some people, I think, last week was how we get from our convolutional layers to our convolutional layers to our linear layers at the end, right? So if we go back to this, if we go back to like the structure of the CNN, right? So like here, like we have our kind of pooling layers here, and then we need to somehow get from here to these fully connected layers, right? And we need that to happen in a way that the dimensions make sense. And there is a transformation, like we have to do a transformation, right? And I'll talk about this, but in general, we have to do some sort of transformation, right? Because remember, the outputs for our kind of convolutional layers and our max pooling layers are volumes, right? Because we have multiple feature maps. So they're going to be volumes. Like I just said, like, for example, we could have 15 by 15 by 6 if we have like 6 feature maps at the end of our kind of convolutional part of the network. And then we somehow need to get that volume into a kind of straight line of kind of like a vector, right? If we remember how the fully connected layers work, it's just a bunch of columns where each column is sort of like one layer in the network, right? And so basically we need all of our inputs to be just a straight line of neurons, like just one vector of flattened neurons, right? So we need to kind of take this cube or this rectangular prism, this volume that we have, and we need to kind of unravel it so that it's just a straight line, right? Because the input that the linear layer expects is going to be a shape that's a straight line down. So if you try to give the linear layer a volume, it's going to give you a runtime error. It's going to be like, look, I don't know how to deal with these dimensions, right? So there's two things we have to account for. The first thing we have to account for is what we need our little material or our piece to look like. And then the second thing is how are we going to use that piece? So how are we going to construct this material? So the material we're constructing here is a linear layer, and we need to determine exactly how many neurons are in the input, right? We can kind of choose like how many we want it to output, right? That's kind of up to us. That's like how many hidden neurons do we want in the next layer, right? We can choose that, but we need this to match the number of neurons that were in the output of this convolutional layer that I have here, right? So we need to figure out a way to do that. So the way we do that is we just compute sort of the volume, right? So for example, in the case that we had 15 by 15 by 6 that I keep bringing up, like then you would have whatever 15 by 15 by 6 is. I can just do that. 15's 225 times 6. Yeah, so it would be 1,350, right? So you would put 1,350 here because there's 1,350 neurons that have to be accounted for that are going into this linear layer. Okay. In my case, I have 16 feature maps, and then my height and width of each of my feature maps is 5 by 5. So I do 16 by 5 by 16 times 5 times 5. So I kind of compute the volume. And then that's how many, that's going to be the number of neurons in my input to this linear layer. Okay. Does that make sense to everyone? Can I get a yes or a no in the chat if at least that part makes sense? I haven't talked about how we're going to transform the data yet. I've just talked about like how do we know how big the linear layer needs to be? Okay, I got one yeah. I would like more than one yeah or at least a no or something. Yeah, I mean, yeah, so here, don't worry about the super like I don't know what you mean by low level. Like this is all pretty high level, right? Like the idea, like what's nice about this is that like PyTorch handles the low level details for you, right? Like what you need to, all you need to worry about is like making sure like the output for a certain layer matches the input of the next layer. So for example, to show that for the next layer, right? So this linear layer, my first linear layer outputs 120 neurons. So that means that my next linear layer needs to take in 120 neurons, right? If these two values right here don't match, then you won't be able to pass the output you get from this thing into this thing, right? And same goes for the second linear layer to the third one. Like if I have 84 hidden neurons here, then I also need to have 84 going here because these values need to match. So in general, like these values just need to match. So I think most of us get that those values need to match. Now, let's look at the forward function because this is where it's like a little bit more confusing, right? So the forward function is where we actually like put all of our materials together, like how we put our Lego pieces together, how we want to construct the model itself, right? So like what this is saying is first pass my input through my first convolutional layer. So self.c1x is going to be the output, is going to give us the output of my first convolutional layer. Then I'm saying apply ReLU to that. And then I'm saying apply max pooling to that. So if I go here, basically the self.c1 is we get this kind of convolutional layer. And then we pass it through ReLU. So we go from convolution to ReLU, and then we do max pooling on that. It's exactly in the same order that we talk about here, right? So if we go back to it, we pass it through the convolutional layer, and then we pass the convolutional layer through our ReLU activation function, and then we pass that through our max pooling layer. So what this one line does is three different things that I need to make that very clear to everyone. It does three different things, right? First, we pass it through the first convolution layer, then we pass it through ReLU, and then we pass it through max pooling. So we did three things. So you could have also written that one line as like x equals self.c1x. Then you could have said x is f.ReLU x. And then you could have said x is self.pool.x. So this first line here is equivalent to like writing these three things, right? So first I pass it through the convolution, then convolutional layer, then I apply my activation function, then I apply pooling. Okay. And then this line right here, now I pass it through my second convolutional layer, so self.c2x. Then I pass through my activation function again, and then I perform max pooling again. Now, notice how I pass it through C1 here, and then I pass it through C2 here. But then these other two things were the same function each time, right? Now, the reason it's the same function each time is, like I briefly mentioned this last week, right? So, like f.ReLU is just a function, right? It's always going to be doing exactly the same thing, and it's not special. There's no like weights that it has to learn. It's just a straight computation. Same thing for max pooling. There's no weights that we're learning, right? It's a strict rule. You have a stride. The strict rule is you have a stride length of 2 here. You have filters that are 2 by 2, and you're always going to take the maximum value in each of those 2 by 2 local receptive fields, right? You're always going to do that. So there's no values that we need to learn. It's always going to perform exactly the same operation. So that's why we can just use the same instance of this function. The reason why we have a separate C1 and a separate C2 is because those are actually different convolutional layers, right? They're distinct functions from each other. The first one is the first convolutional layer. It's this guy that takes in something that's 3 color channels and it outputs something that's 6 channels. And then this guy takes something that's 6 channels and it outputs 16 channels. So they're doing different things, right? And each of them have their own set of weights that they need to learn. So these are distinct functions from each other. So that's why we have like a separate C1 and a separate C2, but this ReLU and this pooling is the same thing. So is it clear? Is it at least sort of clear to people like when we need to like define like a different like layer and when we can just use the same layer? Because like this self.pool right here is just this one and then .max pool, but over here we have like a separate self.c1. It's this thing, and we have a separate self.c2, it's this thing, right? So they're different. So is it clear to everyone like why I need to use like different like C1 and C2, but I can use the same ReLU and max pooling? Okay, okay, nice. I greatly appreciate when you guys all when more people respond. So thank you. Okay, that is good. Okay, so now let's talk about yeah, we need to speed up a little bit, but let's talk about this x dot view. So like I said, we need to unravel the volume of neurons that we get, right? So remember, this outputs right here at the end of this. Once we've made this assignment here, we have x is some tensor that's like a volume, right? It's like a volume of neurons, right? But we need to flatten that volume of neurons out into a straight line, so it's compatible with the linear layer. So to do that, I use this thing called x dot view. You could also do x dot reshape. It's the same thing. It's just like a slightly different template. So basically, I reshape it, and then I say I want my innermost dimension to be 16 times 5 by 5, right? And we hopefully understand where we get this number now, right? Because like I said, the number of outputs, the number of neurons we actually have coming out of this last convolutional layer is 16 times 5 by 5, right? So we need that many neurons in our inner layer, and then we just want to flatten everything out. So like I mentioned last week, if we put a -1 here, it'll automatically interpret basically what the dimensions of the other things need to be, right? Like all we care about is that the innermost dimension has all of our neurons in it, because that way it's basically just a vector, right? It's just a flattened out vector of neurons, and then we can let PyTorch kind of deal with the rest of the dimensions. Okay, so this is a very crucial kind of step to make sure we do. And then after, so what this, like I said, I'll repeat it one more time. This will take the volume, this line takes that volume of neurons that we had and kind of just flattens it into a straight line. So once we have the straight line of neurons, then we just pass it through our linear layers, right? We pass it through the first linear layer, apply ReLU, pass it through the second linear layer and apply ReLU, and then pass it through our last linear layer. And the reason we don't also apply like ReLU or an activation function here is because I think I mentioned in the PyTorch workshop, a lot of times our criterion or the cost function that we'll use later on automatically like applies an activation function to the input that it receives. So that's why a lot of times you don't explicitly see people calling an activation function at the very last layer. Okay, so is there any questions about defining sort of the model architecture? Hopefully, like I think most people were around here. So hopefully like that's clear now. If you guys were like stuck or something, like hopefully like I don't know, did what I just went over like help you guys fix any problems or like fix whatever problems you were having with your guys' networks? Or like how many people like are like on their like project or whatever that they've like gotten up to this point? Okay, so at least a few people have. Same. Okay. Okay. Looks like most of you guys have done this. Okay. I've gotten past it, but I don't know what if my error has to do with this block. Okay. Yeah. I mean, yeah. I'm sure like some of you guys like went ahead and like I encourage you guys to kind of try to implement the rest of it on your own. So hopefully some of you guys did that. And like I said, if you guys are running into errors or whatever, like that's why we're here right now. So we're gonna like go over the next few things step by step together, and then hopefully like it'll help you guys fix any errors. And I'll kind of explain each line of code as I write it, and we'll spend some time talking about each line. So then hopefully it'll all make a lot of sense by the end. Okay. So I'm gonna now create a new code block, and I'm going to be asking you guys a lot of questions because I don't want to just write everything out, because I want it to be sort of collaborative, like we do this together. So I'm going to ask, can someone unmute or say in the chat what kind of the next step usually should be here, now that I have my data and I've defined my architecture and whatnot? Anyone? Okay, yeah, I see some. Okay, yeah, I'm seeing good answers in the chat. So yeah, we need to create. So yeah, there's a few things we need to do. One, we need to. The first thing is we need to create an instance of the model. So nice. Yeah. Okay. So we caught everything in the chat. Nice. So first thing is we need to create an instance of the model. A second thing we need to do is define our criterion, which is like our loss function. And then the third thing we need to do is define our optimizer. So yeah, we need to do those three things now. So let's do that. Let's create an instance of our model. So I'll just call mine model, and I'll just yeah. So we don't take any. So at least my model doesn't take any inputs to the constructor. Your guys's might, if you were doing some cooler customizations with it. But mine doesn't take any input. So let's just create an instance of it. Now, one other line I'm going to add here is model.toDevice, or device is lowercase. So what was device, right? Device we defined up here. It's either a reference to our GPU or a reference to our CPU, right? So I'm going to say model.toDevice here because I need to allocate all of the tensors that are contained in this instance of my model to either the CPU or the GPU. Because if I'm trying to if I don't do this and then later on I send some of my tensors to my GPU, for example, but my model is on the CPU, then it's not going to work, right? So we need, like I said, like I've mentioned multiple times, we need everything to be like everything that's going to be interacting with other things needs to be on the same memory, same area in memory. So on the CPU or the GPU. So I'm going to send my model over to my device. So I'm using my CPU right now. So this will just keep it on the CPU. But if I was using a GPU, and any of you guys who are using a GPU and you want it to train on the GPU, you definitely need this line here. Okay. So now I'll define my loss function. So I'm just going to use cross entropy loss again. So as I just mentioned a few minutes ago, when you do this implementation of cross entropy loss that PyTorch uses actually applies softmax to the inputs that it receives. So that's why I didn't apply any activation function to my output of the model, because when I pass it through the loss function, it's gonna apply softmax already. So it's just like redundant if I and like you actually shouldn't do that, right? Because you don't want to apply like two activation functions. So yeah. And then let's also define optimizer. So I'm going to use Atom. I think I used Atom last time. And we just need to pass it. I'm just going to pass it the parameters. And like there's a bunch of other things. Like you have to pass it your model's parameters, right? Because it's optimizing off of the gradients of like the learnable parameters in your model, right? So you need to pass it that. That's like the minimum of what you need to pass it. You can also like pass it a custom learning rate, and there's a bunch of other stuff like this epsilon value. I'm not going to get into that. All of these have default parameters that they've kind of set. So I'm just going to go with the defaults for now. Just like I said last week, it's very important when you're prototyping like a model, like what we're kind of doing here, like we're prototyping a model to classify. First, just get like the bare bones working, like get something working, and then you can kind of go in and mess with it more and tune it more, right? So now we've done the three things that you guys all said in the chat. So we created we defined our loss function, we defined an instance of our model, and we defined what optimizer we want to use. Okay, so that's great. Now, what should we do next? What one word answer? Just yeah, train. Let's train. Yes, finally. Okay, we finally get to train. Okay, so the training routine is going to be very similar to our here. Let me bring this over. So this is the MNIST classifier that we did in the PyTorch workshop. So it's gonna be very similar to what we have. Where is it? Right here. Right here in this block. There's a few minor differences that I mentioned last week. Yeah, I'll go through them as I write the code. But basically the main difference is we no longer need to do this reshaping here. Now, can someone tell me why we don't have to do this reshaping? So what this is basically right before we pass the inputs into the model, we have to reshape it, right? So why don't we have to do that for the CNN? Okay, yeah. Do you want to unmute and maybe explain? That's basically correct.
Yeah, so when we're defining the forwarding function for the model, when we reshape, that already happens, and we don't have to do it
Yeah.
again.
Yeah. So, I mean, like, that's basically correct. Like the way I'll say it, yeah. So what Ryan said is we want it in 3 dimensions for our model input anyway. So when we are here, so in our MNIST, when we were doing our MNIST classifier, right, they were all linear layers. And as I just spent a lot of time talking about, the linear layers expect you to have a kind of flattened input here, right? So you need to flatten the input first. You also could have done this step. Now, like, I get this was actually like not very smart for me when I wrote this. When you were if I was to write this again, I would actually do this reshaping in the forward function, kind of how we did the reshaping here in our forward function. I would actually like just do the reshaping like right here at the beginning and then pass it in. But yeah, the idea is these inputs are not if we recall, right, they're 28. This is like 16 by 1 by 28 by 28, the batch inputs, right? We've seen that multiple times. It's like 16 for the batch size, 1 because 1 color channel, and then 28 with 28 height, right? So we need to flatten that out before we pass it into the linear layer because that's what the linear layer expects. Now, that's in contrast to the convolutional layers, right? Because, right, if we look at our convolutional network, the first thing we're doing it is passing it through a convolutional network. And unlike the linear layers, the convolutional network actually wants your input to be 3-dimensional, right? So we don't need to. We're already in the shape that we need to be. For our tensors already in the shape that it needs to be when we're passing it into our network. So we don't have to do any weird reshaping at the beginning. So yeah, great answers from both of you. Okay, so let's write a training routine. So I'm gonna do this. So I'm actually gonna define a function to train my stuff, and we can just invoke the function later. But yeah, so I'm gonna write this line here, model.train. So I think by default models are in training mode, but it's good practice because like we're just defining functions right now. So if later on you invoke a function that sets it to evaluation mode, and then you invoke this later, you want to make sure it goes back into train mode, right? So remember, there's model.train, and there's also, oh, this is not C++, model.eval, right? So model.train basically sets up the tensors to have their gradients tracked. So when you do backpropagation, we're actually tracking the gradients, and so we can actually do backpropagation. But model.eval says, okay, look, we don't care about any of that. We're just trying to see what the model outputs, or we're just trying to see what it outputs. We don't care about updating the weights, right? Because when we're testing the model, we're not actually updating any of the weights at that point. So you want to set it to eval mode just so it'll run a bit faster. So this is just common practice that before we train, let's make sure we're in train mode, and before we test, let's make sure we're in eval mode. So I'll write that line. Now let's write our actual training loop. So yeah, I'm gonna write batch labels in train loader. Okay, so let me explain. I promise you guys that we will go through this line by line. So yeah, so train loader, right, is our iterable object that has our lazy loaded data separated into batches of size 16 in our case, right? So if we remember the structure of a single instance of the data loader, it's gonna have it's a tuple where the first tuple contains a batch of the first element of the tuple contains the batch of inputs, and then the second element of the tuple contains the corresponding labels. Okay, so this notation in Python, if you guys aren't familiar, basically this will automatically like unpack us for each instance in the train loader. Like I said, each instance is a tuple, so it'll basically rip that tuple apart into two separate variables for each instance. So this will basically we're unpacking it such that this batch input will give us batch inputs will just give us a single batch of inputs. So in this case, that's like a 16 by 3 by 32 by 32 tensor, right? So 16 for the batch size, 3 for the color channel, it's RGB, and then 32 by 32 because each of the images, right, are, you can even see it on my screen right here, is 32 by 32. Okay. And then the labels will just be 16 different things, right? Because each label is just like a word or something, or like a number. So yeah. So don't be intimidated by this. All it means is for each instance of for each item in train loader is a tuple, and we can unpack that tuple using this notation. So now that I've unpacked my tuple, the next thing I'm going to do is actually send my data or my data over to the GPU. So we'll do that the same way we sent everything else over to the GPU. Or this needs to be labels. Labels. Okay. So all this is doing is sending over my batch inputs and my batch labels to the GPU. Okay. So yeah, I've discussed this many times at this point, so I'm not going to discuss that again. Okay. Now the rest of it is like almost exactly like how we did it in the MNIST case, right? So first we need to zero out our gradients, right? Because at the each time we want to have a fresh, like, clean slate for our gradient, right? Otherwise we would just keep accumulating on top of the gradient, which is not what we want. So we always need to clear the gradients first. So that's what I'm doing. Now I'm gonna feed forward. So I'm gonna define this new variable called batch outputs, and then it's just gonna be our outputs. So I'm gonna pass my inputs into my model, and I'm gonna get some outputs, right? So is anyone confused up to this point or has questions about this? Okay. I will assume we are okay so far. And like, please, what do you mean what was the gradient again? So remember, with PyTorch, all the gradient approximations are kind of handled for us in the background, right? Like each tensor has has data that will kind of track that for us. That's an inherent property of PyTorch tensors, and all we need to do is write these functions that'll basically perform backpropagation for us. Oh, what was the gradient? Like, what is it? Oh, like, so if we recall, like the idea for how we're actually learning is that we want to minimize okay, the idea is we want to reach a local minimum or maybe a global minimum of our cost function, right? So to do that, we perform like gradient descent or like some variation of it, and the idea is that each step we compute the gradient. So the gradient is like the direction we need to move, like the way we need to update our weights in order to approach the local minimum of our cost function, right? And if like the whole point of learning is to approach the local minimum of our cost function, because the cost function gives us an or gives us a metric to evaluate how well the model is doing, right? So like if the cost function's value is really high, that means there's a high cost, right? Which means by the definition of how we define cost functions, that means the model's like not doing a very good job of classifying. But if the value of the cost function is very low, then that means there's a very small discrepancy between this batch output, the batch outputs, like the predictions that the model is giving us, and what the labels are, which means the model is performing well. And the whole idea is we want to use the gradients. We need to find gradient approximations and then update iteratively on towards that local minimum using stochastic gradient descent. So gradient is kind of multi-dimensional. Yeah. It's like a multi-dimensional derivative. Sure. It tells you what direction you need to move along your function to basically increase the fastest. So if we take the negative of that, what we want is to decrease the fastest. So we'll take the negative. If I want to be very precise, will you take like that? It takes like the negative of the gradient. Yeah, that's correct, Darren. Okay. So now, so what have we done so far, right? So for a single for a single batch, right? We send our batch inputs and our labels to our GPU. We clear our gradients. So optimizer.zeroGrad. So now we've computed our prediction. So that's batch.outputs. Next thing we need to do, can someone tell me what the next step should be? So we have our predictions. What's the next step? Yes, correct. We need to compute our loss, right? So now that we have what our predictions are, and obviously we already have we had the labels from the beginning. So now that we have what the model thinks the answers are, and then we have what the answers actually are, we have all the tools we need to compute the loss, right? So let's do that. So the only thing, and we once again, the PyTorch documentation will like explain all of these functions and like I think it's important that you guys like for all these functions that we're using or all these classes that we're in creating instances of, it's important to look at the documentation and like kind of what it expects. So like here like the way this our criterion works is we just pass it our outputs and our labels, and then it can compute the loss for us, right? So that's just the way the template works for the criterion. Okay. And intuitively that makes sense, right? Because when we were looking at all the low level math, right? Like all we needed to compute the loss was, okay, what did the model say the answer was and what is the answer, right? Like we looked at mean squared error a lot. So we said like, what's the difference between the label and the prediction number, and then square that, and then sum the value you get for each of those instances, and then that's gives us our mean squared error, right? So that's like one loss function. So now we have the loss. Okay. Now what do we need to do? Someone tell me like the line of code that I should type. It's like basically the same thing as like what we did for the PyTorch for the MNIST example. Okay, yeah, that's correct, Darren. Do you wanna unmute and tell us what loss dot backwards does?
Is it just like it back propagates, like it uses the loss and then it calculates the, forget which one, the errors for every parameter, and then it like adjusts them accordingly?
Yeah. So this line basically, this one line right here does like the entirety of like the second workshop that we spent like 2 hours going over, right? So this does like all of it, right? It'll like there's many different ways to implement backpropagation that you'll get the same result, but the way we explained it, right, is that we can define some error that's inherent to each neuron. You calculate the errors, then you can use that to calculate the partial derivatives of the cost function with respect to the weights and the partial derivative of the cost function with respect to the bias. And that's ultimately what the approximation of the gradient is, right? It's just a function of the partial derivatives of the weights and the biases, right? So it basically calculates all of that. It'll basically at the end of loss dot backwards, we'll have stored internally all of the partial derivatives for the weights and the biases. So we've stored them, and then the last thing we need to do is perform one iterative step. So a step is basically one iterative update to the weights and biases, right? So as I discussed, like the idea is we're using some sort of variation of like stochastic or gradient descent, where on each iteration we approach like the local minimum. We take one step closer to the local minimum, right? So that's what the optimizer.step does. It says according to the rule that our Atom optimizer entails, take one step based on the values of the partial derivatives for the weights and biases that we just calculated in the previous line. Okay, so now we've completed like basically one weight update, right? So this coincides with like what we've learned in the past workshops, where basically we are going to update the weights and biases at the end of each batch, right? And that's exactly what this code does, right? Because one iteration of this loop is one batch, right? Because batch inputs is one batch labels is one batch. So at the end of this iteration, we do one update. And then after all of our batches, wait, can someone make sure the person who keeps joining the waiting room is getting in? I'm admitting them, but I don't know if there's some sort of problem because they keep asking to join the waiting room. So yeah, if Ben or Justin or someone can check up on that. Okay. Yeah. So when we invoke this train function, or yeah, when we invoke train, right? So we just wrote a function train. It'll basically perform one of what? It'll perform there's a vocabulary term we learned to talk about what it's called when we do all of this one time. So what is it called when we go through all of the data one time? Does anyone remember? Yeah, okay. That's correct. It's an epoch, right? So every time we invoke this function train, it performs one epoch, right? So every time we iterate through all of the data one time, we've completed one epoch, right? So this basically function, when we call this function, it'll do one epoch. So we can write a function that's like for like this many epochs, like run train, right? And then it'll run it for however many epochs we want. And we'll do that in a bit here. But let me also write one more line here, just so we can make sure we're monitoring our loss. So I'm just writing this, or this parenthesis needs to be here. Okay, so this line is just saying it's just telling me to print out the loss at the end of every epoch. Now I'll actually like break down like the syntax of this, maybe in case you guys haven't used Python that much. So when you put a comma in between a print statement, it'll actually append the two things together with a space between them. So this basically will say end of epoch loss. Like when you'll see when we print it out at the end, it'll be like end of epoch loss, and then they'll implicitly it'll add a space, and then it'll concatenate like this result. And Python's nice, so it'll like automatically like cast it to like a string or whatever, and it'll like work out. And round like you can probably imagine what this means. So loss.item, so it just takes the value of the loss and it rounds it to 3 decimal places. So this just prints out the loss at the end of every epoch. We're printing out the loss, right? Because this is not in our little we only print this one time, which is at the end of train, right? So this is the end of epoch loss, right? So yeah, this is our, so we made significant process in our training routine. Okay, cool. Now sorry, give me 1 second. Okay, so I wrote a function that can basically train the model. Now I'm going to write a function that can evaluate the performance of the model. Okay, so that's the next step we're going to do. And then we'll like actually like write like the line that you guys like expect, like for epoch, like this. So I'm going to invoke train. So in this case, I'll invoke it 6 times, or I guess 5. Yeah, 5 times. Yeah, because it doesn't include the 6. So 1, 2, 3, 4, 5. So we run this for 5 epochs, and then I'm also gonna write this function called test right now before we care about this one, just so it's just better coding practice, you know. So first thing I'm gonna do is I'm gonna define this array as a template for just so we can more clearly see how the model is performing. So let me just write this out real quick. Horse, ship, truck. Okay. So basically, like, the labels are numbers. They're not strings. And each label corresponds to like a certain object, right? So like with the handwritten digits, like this was not necessary, right? Because like the number that the label is like actually what the output is, right? Like if the label is 0, that means it's literally the digit 0. But here, for Cypher 10, if your label is like a 0, that corresponds to a plane. And if your label is the number 1, then it corresponds to car. If it's 2, it corresponds to bird, so on and so forth. So I'm defining this just so when we're trying to visualize how the model is doing, we can kind of like if the label is like 0, then we can say like class is 0, and then we'll know that that's like planes, right? Hopefully it makes sense why I did that, right? Just so I can translate the number into what it actually is for our purposes. Okay. So, okay, I'm going to write a function called test, and I'm going to give it one parameter called a loader. So the loader could either be the train loader, it could be like a validation loader, or it could be like a test loader. Basically, it'll just evaluate the performance of the model on like whatever data you pass into it, right? So if we pass in, so if you were to pass, with a function I'm about to write, if you did pass in the train data, it would like evaluate the performance on the train data. So it wouldn't perform any weight updates. That's what the job of the train function is to do. But instead of like testing it on the test data, we could test it on the train data if for whatever reason we wanted to do that, like just to test for like overfitting and stuff like that, right? So it gives us a little bit more flexibility, right? So the first thing I'm going to do is switch our model over to eval mode, because we're no longer, so this function is just not updating any of the weights or biases or anything, right? We're just trying to assess the performance of the model. We're trying to see like how accurate is it, right? So we don't care about tracking any of the weight updates or the gradients right now. So I'm going to set it to eval mode. I'm going to define a variable called correct, and then we're gonna it's gonna be like a counter. So we're gonna count how many things it gets correct, and then we're gonna divide that by the total number of instances we gave it, and then that'll by definition give us the % accuracy that we got, right? So let's do that. And I'll stop in a second for questions, because I know I've been talking for a little while. Okay, I'm actually going to stop for questions right now. So yeah, please ask if you have any. Okay. Are you guys okay, yeah. That's fine. That's fine. We'll just keep going then. Okay. So I'm going to do the same thing that I did before. I'm going to send my things over. So just I know I said I would go line by line. So this is just the same idea as what we did up here, right? But it can be for what. So the loader is going to be like whatever loader we give it. So if we pass train loader here, it'll do exactly the same thing. It'll just parse it over the train loader. But if we give it like test loader, then it'll do it over test loader instead of train loader. It's just a different part of the data. So I'm going to do I can actually just take this line. So I'm going to do exactly this again. I'm going to send my data over to the GPU just because my GPU can run these feeding forward computations faster. I'm gonna compute my predictions. So yeah, so I'm gonna do model batch inputs, and then I'm gonna do argmax axis equals 1. Okay, so this is a bit different from what we did in the training, right? So let's break this down. So when we pass through model.batch inputs, does someone want to tell me the dimensions of this output? So what do we get? What is the dimensions of this tensor right here? Don't pretend that argmax isn't there. So how is the model going to look in terms of the dimensions when we pass it through model underscore batch inputs? So let's look back up here to get a better idea, right? Yeah, so that's okay. That's almost correct, Darren. So it's 16 by 10, right? Because so for each thing, it's like 1 by 10, but there's 16 of them because we're computing the whole batch at once. Just a minor difference, right? Like or not difference, but just like minor correction, right? Like we're passing the model actually like feeds forward the entire batch in parallel. Like it just makes it use of matrix multiplication properties to do this, just so it'll run faster. But yeah, that's correct. Like for each training sample, we get outputs for 10 different neurons, right? Because there's 10 different things we need to classify from. So it'll give us 10 different values for each instance. And then just like with the MNIST data set, whatever value is the highest value, that's the index of that's the index we're going to choose for the prediction, right? So if like the values are like for like a single instance, if it's like 0 0.01, 0 0.03, like 0 0.54 or 0 0.31, let's say 0. Blah blah blah, like then like dot 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 for all 10, and then let's say like the 10th thing is like 0.99, right? So 0.99 is the highest value, right? So we're gonna say, and this value is in the 10th index, right? It's the 10th value. So then we're gonna say our class of the model says the classification is the number 10, right? So, and the number 10, as we just discussed, corresponds to the truck, right? Because index 10 is the truck. So that basically means if in our 10 values that it outputs, if the 10th index is the highest thing, that means that the network is saying, okay, this is a truck. And if the second index is the highest number, that's saying, okay, it's a car. If the third thing is the highest, it's saying, okay, it's a bird. Okay. So that's kind of how we interpret what the network is telling us. So, and that's what we're gonna do here, right? We're gonna extract that information. So we're gonna take argmax axis equals 1. So what this is going to do is give us a list that is 16 numbers, one number for the label for the prediction that each batch gives. And what argmax axis 1 is going to do, because we have 16 by 10 data, so this is axis 0. Axis 0 corresponds to the 16, and axis 1 corresponds to the 10. So we're going to look in here. We're going to look in the 10 area, so sort of in this array. And then we're going to take we're going to return the index of whatever the value is the highest in this axis 1. So argmax axis 1, in this case, we would have like 16 of these, right? Because and then these would all be one tensor, right? So this is kind of how model batch inputs would look. This is like how the outputs look. right? And then when we do argmax access 1, it's going to take, for each of these, it's going to return one number, and the number is whatever the index of the highest thing is. So like here, I just pasted the same thing every time. So, or it would just give us 9 every time. And it would do that 16 times. Okay? Because for here, like each of our things said, okay, it's the 10th. So 9 is the 10th index, right? Because its index starts at 0. So it would say, okay, all of these, it's saying it's a truck, right? So it would return just 16 values, and those 16 values are just the predictions that for each training example in the batch that the model gave. Now, this is useful because this is exactly the same way that the labels themselves are organized, right? We said batch.labels also has this shape of 16, right? It's also 16 where each index is a label for one training example in the batch. So like, I'm not in the right spot. So like here, like batch labels would be like could hold values like 0, 5, 2, like 6, 9, 2, 3, etc. And then this would basically mean, okay, the label for the first example in the batch is 0, which corresponds to a plane. And the label for the second thing is 5, which corresponds to 0, 1, 2, 3, 4, 5, 6. That would be a dog, so on and so forth. So do you guys see how how this line gives us something that we can directly compare with the labels? Do you guys kind of see that? Because we need to directly count how many of these values are equal, right? To get the accuracy. So do you guys see how the idea is we want to basically somehow make some sort of like tensor of outputs from the model that's like exactly like comparable to what the batch labels are? Can I get a yes or no if that's like clear or not clear? Okay. Yeah. So, yeah, I'll just So we'll move on from this line because I spent quite a while talking about it. But just in general, like this isn't even just in CS. It's like just in math in general, right? When you talk about argmax, like when you say argmax, it talks about like the input or like the like the input, like the argument, right? Like you can think about, okay, I'm going on a little bit of a tangent, but I think it's helpful to understand. You can think about an array as like a function that maps values, right? So if you have an array that, like, let's just have a simple array. It has the values 5, 8, and 9. It has 3 values in it, right? You can think of this as a function, and it has indices as always like 0, 1, and 2, right? Corresponding. You can think of this array as a function that maps the value of 0 to the value 5, the value of 1 to the value 8, and the value 2 to the value 9. Right? You can think of it like this. And in this sense, the 0, 1, and 2 are like your arguments. It's like the arg. It's like the input to the function, and the 5, 8, 9 is like the output to the function, right? So the reason it's argmax is the arg references like the corresponding input, right? So the idea was that we looked at the outputs, sort of. Like you can think of the things that are actually in the array as like the outputs. We looked at what all the outputs were, and then we chose what the highest value was. So the highest value was 0.99 here. And then, so in this case, if I want to make it corresponding to one of, to the array we already had, so the value 0 like maps to 0.01, the value 1 maps to like 0.03, so on and so forth. And then the value 9 maps to 0.09, right? So it looks at all of these all of these outputs, and then it's like, okay, 0.099 or 0.99 is the highest one. And then what argument does it correspond to? Okay, it corresponds to the argument 9. So I'll return the value 9. Okay. So that's the difference between argmax and like like model batch inputs like dot max axis one. So instead of returning the arguments, instead of returning the indices, it would return the numbers themselves, right? So instead of returning an array that's like a bunch of nines, because all of these, the max values at index 9, instead of returning that, it would just return what the value at index 9 is for each of them, right? So it would just say 0.099, 0.0999, 0.0, it would do that for all of them, right? So that's the difference between returning max and like argmax, okay? I think that's an important kind of distinction to make. When you read code and you're trying to understand it, it's very important to understand the difference between like when we invoke the max function and we invoke the argmax function. And the reason we invoke the argmax function here is because we want it to be directly comparable to the labels, right? Like our labels right here, the max index, the index of the max value inherently corresponds to what the network is saying the output is. So that's why we want that value. Okay. So I've spent enough time talking about that. So let's move on from that. So now we have that nice array that we can directly compare to the labels. So that's super nice. So then it's easy. So we can increment the number of things we got correct. So I'm going to write this line of code and then explain it. Labels dot sum dot item. Okay. So this code does a lot of things. So I'm actually going to write something that does exactly the same thing. So I'm gonna write some code, comment it out that will do exactly what this line of code does, and then hopefully it'll make it more clear what's happening here. Okay. So let's say for value in predictions. So basically we're gonna go through each thing, each value in predictions. So predictions is the outputs that our model predicted. For each of those, if value equals actually wait, let me think about this. If value equals okay, let's do it like this actually. Let's do it more like a C thing. For I in range length of, so all I'm doing is I'm enumerating over the indices instead of the values themselves, right? So this will just, so I here will be 0, 1, 2, 3, 4, 5, 6. It'll just go over the indices in prediction. So I'm just enumerating by indices so I can compare it with compare the batch labels to the same index in the batch in the predictions. So let me write that. So for if predictions dot I equals batch labels dot I correct plus equals 1. And yeah, so this does exactly what this one line of code. Yeah, these two lines of code do the same thing. It's just this is a more, what I wrote is like a more Python way of doing it. So hopefully it's clear to you guys what this commented out code does. So remember, like our predictions array will just have a bunch of numbers like 6, 9, 9, 2, 4, whatever, right? And then batch labels will be an array of the same size that has like the labels. So let's say our network's pretty good. So most of these values should be the same. Let's say like gets this one wrong. So it's at 2 instead of 3, but it's like mostly pretty good, right? So like, let's look at what happens here, right? So we enumerate over all the indices in each of these two things. Like they have exactly the same length. So I could have just as easily said batch labels here. They're the same length, right? So it doesn't matter. So we enumerate over all the indices, over the indices of these arrays. So if the value at this index matches the value at this, if the value at index 0 matches for the two arrays, then that means we got that one correct. And then we do that for each of the things in the array, right? Is that clear? Like I'll explain how that equals like this in a second, but is this part at least clear? Yes, no, maybe so. Hopefully. Okay, cool. Yeah. So this literally does the same thing. So this will basically give you an array. Predictions equals batch labels. I think it'll give you an array where it's like I'm not exactly sure, but I think it gives you an array that's the same size as predictions and batch labels. And then like if it's equal at that index, it'll say true, and if it's like not, it'll say false. So let's look at the in this toy example that I made. Let's look at what this will look like. If I'm not mistaken, this will look something like this. So true, 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 false, true, etc. So yeah, so 3 equals 3, so that's true. 2 equals 2, so that's true. 6 equals 6, so that's true. 9 equals 9, so that's true. 9 equals 9, so that's true. 2 does not equal 3, so that's false. 4 equals 4, so that's true, so on and so forth. So it'll populate an array where that's the same size as these two, where if the corresponding indices values are the same, it'll be true. But if it's not the same, then it'll be false. Okay. And then what sum does is what you'd expect. So basically the number of trues we have is the number of things we got right? Hopefully that's clear. The number of trues that are in this is the number of things we got right. And as we know, in a more low level setting, the value true is commonly interpreted as 1, and the value like false is like commonly interpreted as 0, right? So when we do sum, basically it'll add 1 for each of the trues, and it'll add 0 if it's false. So it'll basically, when you do dot sum, it'll give you an array that just holds like the number of trues that we had. So like here we have 1, 2, 3, 4, 5, 6 trues. So then this line predictions equals batch underscore labels dot sum. So this will just be, in our case, it'll just be the number 6, right? So it'll be the number of things we got correct. And then dot item, like we said, it just like extracts the item, because if the array or the data structure is like a single value, like the tensor of the array or whatever is a single value, you can just do dot item, and then it'll just like unbox that. So it'll just give us the number 6. Okay. So basically we add however many we got correct. Okay. As you'd expect. So hopefully that's kind of clear what this line means now. So this is an array that holds a bunch of trues and falses. It'll be true if the corresponding index matches, value at the index matches. It'll be false if it doesn't. Then the trues corresponds to 1s and the falses correspond to 0. So we can sum that up to get the number of trues we have. And that's how we know how many things we just got correct, right? So yeah, we just added the number of things we got correct. And now we're kind of done. So now I'm gonna print out end of epoch accuracy, right? So once again, once we go through all of this, we've finished like one epoch. Like we went through the data once. We're not training, we're just evaluating stuff. So I guess epoch might not technically be the correct terminology. I don't know if epoch only applies to like when you're training, or if it doesn't matter. You guys get the point. So after we've gone through all the data once, like how accurate like was our model, right? So how are we going to do that? So basically we have the number of things we got correct. If we divide that by the number of things we got, but if we divide that by the total number of things that we tested, and then we multiply that by 100, that gives us our % accuracy, right? Hopefully that's clear to everyone. So yeah, let's just do that. So 100 times the number of things we got correct over the length of our whole data set, right? So we know for a fact that we've gone through exactly this. We've tried to predict exactly this many things, right? Because we went through exactly every example in the data set one time. Or I guess this should, okay, yeah. I guess this should actually say loader, because we might not use the test data set. Yeah. Okay. And then I'll just say percent at the end. Ooh, okay. Yeah. So, right, we take the number of things we got correct, and then we divide that by the total number of things we multiply by 100. So that's our accuracy, right? Hopefully that's clear to everyone. I'm also going to write a little bit more to kind of visualize what's going on. Okay. So let's do it like this. Length batch labels. Okay. And then for each of those, so I want to print out for some of our examples, I want to print out every once in a while, I want to print out like a few images, and then I want to print out like, I showed you guys this last week. I want to print out a few images, and I want to print out what the model's guess was, and I want to print out what the actual label was. Okay, and this is where we're actually going to use this classes array right here. So okay, I'm actually gonna move all this stuff down here, so just so you guys can see the full code a bit more clearly. Okay. So yeah, I'm gonna say, so here's my guess. So my guess will be classes predictions I. And then I'll explain this. Just give me 1 sec. And then label classes batch labels I. Okay, so, and then I also am just gonna print out the image just like we did before. So this is exactly what we had up there, right? So I just want, so I can also see what the image actually is, right? So let me explain this line, right? So predictions.I. So remember, predictions is an array that holds 16 values. So like, yeah, it holds 16 values, and each of them is like the label for one instance in the batch, right? So we want to go through every index in, and then same thing for labels, except it's like the correct things, right? For example. Okay. So yeah. So if we take predictions I, so we'll start at 0, right? So let's say we're looking at the first iteration of the loop. So I will be 0. So predictions at index 0 is the value 0, right? So that means the label that we want is the one corresponding to index 0. So that's plain, right? So if we pass in classes, so predictions I gives you the value 0. So if you pass classes this at 0, so the first thing in classes, it'll say plain, right? And that corresponds to the value plain. Because if our label or our prediction is the value 0, like I mentioned earlier, that corresponds to the value plain, right? So I'm just translating these numbers into what the actual labels are, right? That's all I'm doing. Isn't lang loader the number of batches? Yeah, you're right, Darren, you're right. So I guess that needs to be times 16 in this case. Good catch. Yeah. So that's actually all of the code I kind of wrote for this. So yeah, now we all we did was write functions. Now we actually have to call the functions too, right? So let's quickly go over what this does, and then I'll actually run everything, and we'll see it happen. So we want to run for 5 epochs here. So range 1 to 6. We start at 1, 1, 2, 3, 4, 5. So at each epoch, I want to do a training. I want to train the model over the data once. So we'll call train. And then I also want to evaluate the performance of the model on the test data after every epoch. You could also just do this at the very end. Like I could also just do this. So I could just train it 6 times and then I could see it at the very end. But it's nice to usually see how you're doing on the test set, like over time, after every epoch. So you can sort of monitor like, okay, is my model overfitting? Is it doing stuff like that? Now we haven't actually written any graphs that like, or code. We haven't written any code that will like actually graph the loss. So we don't have a good way to like see if it's overfitting. But in general, you want to be monitoring these things while you are training the model. Like don't do it everything. Don't only test it at the very end, because then you won't be able to really see like at what point did my model start overfitting, right? Like if I started overfitting after like 10 epochs, I won't know if I didn't like check after every epoch, right? But anyway, let's run this. Hopefully this doesn't explode. If it does explode, I have a key that, I mean, I was just writing the stuff off the key that we wrote earlier, but so this should work. Let's just run all, see what happens. Is it stuck? What is happening? Wait, let me run this block by block and see what happens. Okay. Okay. Did I have a typo somewhere? Where did I say models? Do you guys see it? Oh. Okay. Okay, I think it works now. So yeah, it'll take a second, right? Because it takes a second to train for each epoch. But hopefully after a second. Okay, yeah, that's what I thought. So you can't do this. So we're passing the test data set anyway. For now. We'll look into this a bit more as to how we can kind of make this coincide to our loader in a second, but let's see if this works. Okay, yes. Awesome. So we got end of epoch loss. We got our accuracy on the test data set after the first epoch. And then I think I think the way I did it is for, yeah, so this is actually going to print out a lot of things. So let's look at some of these, right? So I got this one right. It said it was a frog. So keep in mind, right? It's like, it's doing pretty well even after the first epoch, because if we were guessing blindly, we would have 10% accuracy, right? Because there would be there's 10 classifications. There's 10 things to guess from. So it's already at 53% after one epoch. So that's pretty good. So it says this one's a frog. So we guessed it's a frog. It got it right. We say this one's a ship. It got it right. So this one guessed that it was a deer, but it was actually a frog. I mean, I can barely tell that's a frog, so I don't blame it. Got the car right. So yeah, this one's hard, right? So I thought it was a cat, but it's a dog. That's pretty hard considering how low res the images are. But yeah, it's cool how you guys. Yeah, I think it's pretty neat, right? How if you know how to kind of work with the data, you can kind of actually see like, okay, is it getting it right? Is it getting it wrong? And then you can actually see the image for yourself. So I think that's pretty cool. Now, I'm going to actually comment out this line or this portion and then run this again. Yeah, and then after this, I want to, so we only have 15 minutes, but hopefully like you guys, after I've gone through everything, we're able to like identify any errors you had in your guys' code. And if you don't, we'll take the time to kind of look at that. And then I also want to see if anyone can like beat the accuracy that I got on my machine with their model. So yeah. So do you guys like have something? Are you guys able to like run it? Are you guys still getting errors of some sort? Okay, I got one person who, yes, I can run mine. Okay, at least two people. I'm still working through an error. Yes, I was able to run one. Okay, now I think at this point, so I'm going to say a few last words for the people watching the recording, and then I'm going to, I think we should end the recording here. And then we can kind of work through a few errors that few of you guys may still be having, and then we can, and then if you guys don't have any errors, while we're trying to help the people who fix their errors, can you guys try to see if you can beat my model? So I got 60, almost 61%. So yeah, try to play around with hyperparameters, the learning rate, the number of like layers that you have, the loss function, and see if you can beat 61%. Okay. Now, before we stop the recording, I'm just going to say a few last words. So if you guys are here live, don't leave yet because we're going to do the things we just said. But yeah, for everyone tuning in on the videos, thank you so much for coming out to Advanced Track. We really appreciate everyone who's watched our workshops. We spend a lot of time on them, and it means a lot that you guys come out, and it's really fun that we get to do this with you guys every week. Just a reminder, we are going to be doing Advanced Plus Plus next quarter. We highly encourage you guys to come out to that. So I think, like I said, probably me, Justin, and Varan, who taught Apply ML this quarter, is going to be teaching that. Probably, no promises, but yeah. So if you like us, please come out. If you hate us, then unlucky. But yeah. So that's all I had to say. Ben or Justin, do you guys have any closing remarks?
Oh, just
Yeah,
echoing the same thing. But yeah, go ahead, ask Justin.
Yeah, just wanted to say thank you one more time to everyone joining us asynchronously. We do have a feedback form, so if we could get some feedback for the last workshop, we'd also appreciate that. But yeah, thank you for sticking with it. We really appreciate your support in bringing you guys this content and sharing something that we're all passionate about.
Yep, I have the feedback form on the screen for you guys here. For everyone watching remotely. Yeah.
And if you guys want, you can also leave feedback for the whole track as a whole. Like if you've learned something or you felt like we went too slow overall, not just the specific workshop, this would be the time to leave that feedback too. We really appreciate it. Thank you.
Yeah, we tried a lot of. Not only was it online this quarter, we also changed Advanced Track a lot since the last time we taught it. So like this project didn't exist. So yeah, we realized there might be some small bumps and some things we could have done better, of course, as the first time doing anything. So yeah, we always appreciate that. So yeah, I guess Ben, you can end the recording, and then we can help out with some errors.
All right.